Okay, so now let's get into the third part, which is the counter integral of analytic complex function. So before we start, we need a few preparations. First is the Cauchy-Riemann equations. I've written them in here. And the second is the 2D divergence theorem. Consider P and Q to be like smooth 2D, like the two variable functions. In this case, if in the 2D like x or y plane, I have some closed contour L in which it encloses the area sigma, and I always have this identity. This is the 2D divergence theorem. If, unfortunately, either the functions have some singularities, then I can just take those areas out. So it has some blotches in here, and the sigma is enclosed within the big loop of L, but outside some smaller loops of L1, L2, L3, all the way up. And in this case, we also have the 2D divergence theorem, but the integral has to be like, for the outer loop, it has to go counterclockwise, but for the inner loops, they all have to go clockwise. So in this case, I add the direction of the integral, which we have to be very careful. Okay, so let's apply all these to the integral of complex function. Think about whatever loop it is, and in which it encloses an area sigma. Consider fz be an analytic function in sigma. So the derivative of f exists at all points in the sigma. There's no singularity at all in here. Okay. So in this case, we would say, consider this integral. We do the integral in the direction of L. For the definition of this integral, it's like I evaluate the function value of fz along this loop. For example, at this point, I evaluate fz, and I evaluate what this dz is, because we have the complex plane, and this little segment, of course, it corresponds to some complex number whose absolute value is infinitely small. So I can evaluate fz, I can evaluate this infinitely small complex number dz, and I multiply them together, I get some sort of complex number, infinitely small complex number fz dz. And I just do this for the whole loop, and I add all these fz dz up. That becomes the integral. Okay, so with this definition, let's see. Suppose that we can write this f in terms of Casset plus I eta. Further, suppose that we can write dz in terms of dx plus I dy. Okay. Now, let's expand this. This is Casset times dx. And we also have these two terms. This is I times I gives -1, so we have eta dy. Okay, this is the real term. Let's look at the imaginary part. So this I eta times this dx, this I dy times this Casset. So that gives I integral of eta times dx plus Casset times dy. Okay? Now, let's use the 2D divergence theorem to rewrite the integral. Instead of line integral, let's write surface integral. So, cosec and q is negative eta, right? So, q is negative eta, p is positive cosec. Plug it in here, negative eta, positive cosec. That's literally negative these two things, dx dy, plus I surface integral of. Now we flip them. This is eta, this is cosec, so this is cosec, this is eta. Okay, and at this step, something interesting is going to happen. Look at the CR equations. Partial cosec over partial x equals partial eta over partial y. So partial cosec over partial x, partial eta over partial y. That's exactly the same thing. This term cancels. Partial eta over partial x is negative of partial eta over partial y. So here, we can just replace this negative partial eta over partial y with a positive partial eta over partial x. So this term is also 0. This term also cancels. So we get a very nice result. This is simply 0. This property is very, very important, and it's very unique to complex analysis, because we would never imagine like a real function to have such nice property. But when fz is complex function and if it is analytic in some region, then if we do the integral along the boundary, the integral result is always 0. For example, I can say cosine z dz maybe along this circle. Let's say like along the circle. For example, this is 2 and the radius is 1. I would say z minus 2 absolute value equals to 1. I'll just let you do the integral along this circle. If you really expand it, if you really focus on definition, that's going to give you very, very big trouble. But we know that cosine z is analytic throughout the whole complex plane. So instantly, I could just say this equals to 0 without actually doing any calculation. Okay. So this is the simple case. Now, what we have is this equals to 0. Let's consider some more complicated cases. For example, in the complex plane, there's a big region. There are small loops like this. And I say the function is analytic in region like this. Inside this big loop, but outside the small loops. This is L, this is L1, L2, and L3. And all the way, for example, there are other loops. And in this case, based on the 2D divergence theorem, just replace this one integral into this integral. So I would conclude that counterclockwise is fz dz plus clockwise fz dz over all this. This is on the big loop, this is on the small loops, and that has to equal to 0. Okay. Of course, if we flip the direction of the integral, for example, from clockwise to counterclockwise, we are actually flipping the direction of dz, or equivalently, we are multiplying a factor of -1 on it. So if I flip it, okay, if I do this, then I'll just write a negative in here. So for this conclusion, I can write it in an equivalent way. It's just that the integral of this big loop equals to the sum of the integral still in counterclockwise direction along all the inner loops. Pause. Okay, now let's dig into this a little bit further. Think about a complex function that is analytic in some region. Let's pick up arbitrary 2 points, like from z1 and z2, inside this region. So fz is analytic inside the big region sigma. So we can conclude that for any closed loop inside this region, this contour integral has to be zero. So now let's picture two different routes from z1 to z2. This is L1. This route is L2. Okay, like this. Of course, we have to guarantee that L1 is inside the loop. L2 is also, inside the big region. L2 is also inside the big region on which fz is analytic. So L1 and L2, if we flip the direction of L2 in this way, then L1 and the flipped L2 would form a complete loop. So the integral along L1 of fz dz, I said we just flip the direction of L2, right? So compared with the real integral along root L2, we flip the direction to make a full loop, closed loop. So over here, it has to be a negative sign to take care of the flip. Now this is the integral of fz dz over the full loop, for which we know it has to be zero, and obviously we can just rearrange the equation this way. So for arbitrary root from z1 to z2, as long as the root is like inside the region where fz is analytic, then this integral, the integral from z1 to z2, does not really depend on the root of integration. So in this way, for some analytic functions, we can still write the antiderivatives. For example, we know that sine z, cosine z, like e to z, we know that these functions are all analytic in the whole complex plane. So we can write sine z dz as like negative cosine z plus some constant. We can write cosine z dz equals to sine z plus some constant. We can write integral of e dz or dz equals to just ez plus some constant. But of course, all variables here, all functions here are complex instead of real. Stop. Okay. So now let's do an example. Let A be some arbitrary complex number. And let L be a closed loop enclosing A. So that is, suppose we have a complex plane, and for example A is here, and let's think about an arbitrary loop like this. A is enclosed in the loop. Now let's evaluate this. I'll call it In. Means the loop integral of z minus a to the power of n dz, where n is an integer. It could be positive or zero or negative integer. Okay, so to do this problem, obviously we have to classify n into different types, because the situation is not going to be exactly the same for non-negative n and negative n. So case 1, if n is greater or equal to 0 and n is integer, obviously the function z minus a to the power of n is analytic on the entire complex plane. And when n is integer, there is no such thing as a multi-valued function in here. So basically, the function is very, very well behaved, and from the property of closed loop integral of an analytical function, we could instantly conclude that this in is just 0. Okay, no problem. Here's number 2. If n is smaller or equal to -1. So, in this case, we observe that z minus a to the power of n actually blows up at z equals to a, right? It blows up because we are raising it to negative power. For example, z minus a to the power of -2, that's 1 over z minus a to the power of 2. When z equals to a, it obviously blows up. So, this point is problematic. It creates problem for us. But other than this point, for the rest of it, we can still say that the function is analytic. Anyway, it is elementary function, right? Basic elementary function. So still analytic, and we would say, if we really want to do this integral, the proper way is to find another loop, like enclosed in this L, such that the integral is kind of easy to evaluate. So think about this. We set up a closed loop in the counterclockwise direction like this. I'll just define this loop to be C of epsilon, which is z minus a absolute value equals to epsilon. And obviously this corresponds to a circle centered on this number a with a radius epsilon. So we know that this point is problematic. So from the property of the integral of analytic complex function, we could say that this integral along this arbitrary loop has to equal to the integral along this loop, this very regular, very nice shaped loop like this. And I'll say z minus a to the power of n dz. Okay. So let's see. The function z minus a to the power of n is only not analytic at this single point. Outside this single point, it's analytic everywhere. So, based on our previous discussion, at least along this loop, I can still define, like just do the integral like in the same way as if it was like a real integral, right? Because other than this point, it's all analytic. So I will just treat z as if it is a real number, and I'll just do this integral as if I am doing the real one. And we know that the antiderivative is like n plus 1. This is z minus a to the power of n plus 1. But this is only true when n doesn't equal to 1, -1, right? Otherwise, the denominators go to log. Okay. But when n is -1, we are literally doing the integral like this, right? And the original function, the antiderivative, ln of z minus a plus some constant, right? Okay. So I'll write it in here. So we're doing this for the whole loop. Now we have to think about a way to represent this whole loop, right? So on this loop, the radius is always epsilon, it's fixed. The center is here, And we can think about moving the x and y axis such that they center on the point A. You can think about some artificial axis that's parallel to the x and y axis, and it's centered on A. In this way, this number is z minus A, right? So because it's a circle with radius epsilon, we can obviously say this is z minus A equals to epsilon times e to the I theta, where 0 is smaller than theta smaller than 2 pi, right? Here is theta equals to 0, and all the way theta equals to pi, and when you go back, that's theta equals to 2 pi. So we can say that here, z equals to a plus epsilon. Here, z equals to a plus epsilon times e to the ending point, I times 2 pi. Over here, it's the same idea. Okay, so some people may be curious about why I am writing these two. These two numbers seem to be exactly the same thing because e to the power of I 2 pi is actually 1. So it seems that this number and this number is exactly the same. But always remember that we are talking about complex functions. And sometimes you would encounter multivalued function, and that is going to create issues for us. Let's see. If we look at this function, there's no problem. Because anyway, when z is not negative 1, it has to be negative 2, negative 3, negative 4, negative 5. So it is just, this is literally just 1 over z minus a to some positive integer power. It is not a multivalued function, and we're all good. But let's look at this. This one, z minus a, literally goes from epsilon to epsilon times e to the I 2 pi, right? So if you're talking about this function, it's not multivalued function. These two are the same thing. So basically, this cancels. This will give you 0. But this one, we are literally talking about the ln of epsilon times e I times 2 pi minus ln of epsilon, right? So that's just the ln epsilon plus ln of e to the power of I 2 pi. That is just the 2 pi I. Minus this one is ln epsilon. This one cancels. So we are left with 2 pi I. Right? So this integral is 2 pi I. Okay. And it is exactly this 2 pi I that is going to lead to the residual theorem that we're going to introduce in part 4. Now let's collect the result. I would say In equals to, as long as your n is not negative 1, whether it's positive integer or negative integer or 0, I don't care. It's just 0. But when n is negative 1, the integral is actually 2 pi I. Okay, so this is the end of part 3.